My name is Münchmeyer, and I'm a PhD student at the GFZ Potsdam, the German Research Center for Geoscience. Today, I'm going to talk about the Transformer Earthquake Alerting Model, a model that improves earthquake early warning using deep learning. Earthquake early warning has long relied on two strategies: source estimation and propagation estimation. We introduce a novel strategy using deep learning with the Transformer Earthquake Alerting Model, or short, TEAM. TEAM outperforms prototypical examples of both classical strategies considerably across different hazard scenarios. Let me introduce the traditional approaches. The first one is source estimation-based warning. I'll discuss the traditional strategies using the Tohoku event of 2011. What we see on the map is that the P wave has yet reached a few stations, but the S wave has not. The idea of source estimation-based warning is to take the first P wave recordings to estimate the source parameters, for example magnitude and location, but it might also be a finite fault solutions. Based on the source parameters, a ground motion prediction equation, a GMPE, can be used to predict the peak ground acceleration, PGA. This leads to very early PGA estimates because one only needs the first P wave arrivals, and therefore it leads to long warning times. On the downside, this includes two modeling steps. First, one for source parameter estimation, and the second one, the GMPE for PGA estimation. Both will have simplified assumptions, and that will leave a certain aleatoric uncertainty in the PGA prediction. In addition, often the source parameter estimation schemes saturate for the largest events, and therefore will underestimate the extent of shaking for the largest events. The other common strategy is propagation-based warning. The idea is that when strong shaking is measured at a station, the warning is disseminated to nearby targets, because similar strong shaking is expected at nearby targets. We see this, for example, on the city of Sendai here in the map, which is warned because the S wave, which is measured at the close-by station. This is good because it leads to high accuracy for large events, and also it does not have any saturation for large events, because it directly looks at the shaking instead of trying to estimate magnitude. The disadvantage is that it leads to considerably shorter warning times, because warnings can only be issued once strong shaking, so usually the S wave, arrived at a nearby station. And in examples like here on the bottom, for the Fukushima nuclear power plant, the warning times can be very short, for example here because of the coastal location of the Fukushima nuclear power plant. Now, the source-based estimation has a global view of the event, but lacks the local aspects, while the propagation-based warning has only a local view but lacks the global aspects. We wondered if both could be combined, global and local aspects, and we came up with the idea of using deep learning for early warning to build a system that has both a global and a local view of an earthquake. The input to our system are raw waveforms from multiple seismic stations, and the output are real-time warnings for strong shaking. Now let's start off at the input. The input is a set of waveforms at a few stations. It's generally agreed on in seismology that CNNs, so convolutional neural networks, work very well for feature extraction. So we use a set of convolution layers, pooling layers, and after them use a set of fully connected layers to generate features from the waveforms. We use the same feature extraction independently of the station. Now what we get out of it is one feature set for each station, the position of each station, and then additionally we have a certain set of targets that we're interested in, and we want to predict for each target the peak ground acceleration, the PGA. The problem is that between different events, the stations and also the targets might vary. First, over time stations might become available or unavailable, and second, if the event is at slightly different locations, different stations are going to record the event. This is a problem for deep learning, because most deep learning models expect constant size input and output. And this is where the transformer comes into play. The transformer is used to do an attention-based feature combination. What does a transformer do? The transformer is given a set of input vectors and produces a set of output vectors. Notably, the transformer is flexible with regard to the number of input vectors, so it can be used on different sizes of input while keeping the same set of transformer parameters. In our example, the input are the measured features together with the position of the station and the target locations, and the output are features at the targets. How does the transformer do this? For each target, it implies something called attention, to focus on those stations or those measuring stations that are of particular interest for the target. For example, if for target 1 strong shaking has already been measured in the vicinity, it might use this information to estimate the shaking. If in contrast for target 2 no strong shaking has been measured in vicinity, it might resort to using the global view, looking at stations that best describe the event in total. What we then get out is one feature representation for each target. And from these feature representations, we still need to get to PGA. And to do so, we use mixture density networks. Mixture density networks output, instead of a point estimate as common in regression, a distribution estimate. And they do so by providing parameters, mixture weights, mean and standard deviation of Gaussian random variables, which allows them to describe complex distributions. As for the feature extraction, we apply the same mixture density network to each target. We now have all components to look at the early warning workflow with team. We do so by looking at the 2016 Nocia event, a magnitude 6.5 event in central Italy. The first step is event detection. This is not handled by team itself, but this describes the input to team. What we see in the example image is the extent of the P waves as a dashed line and the extent of the S waves as a solid line, 2.5 seconds after the first P wave arrival at any stations. So the S wave was not yet recorded, but we see the P wave recordings on the right, color-coded to match the stations on the left. These waveforms, together with the station coordinates and the coordinate targets, are then passed on to team. Team applies first the CNN for feature extraction, then the transformer for feature combination, and lastly the mixture density network to get PGA probability densities. It provides one PGA probability density for each target. Now for warning, we need to decide whether there will be a warning or there won't be a warning, and currently we only have those probability densities. You see the densities again color-coded, matching the stations on the left. To decide whether we issue a warning, we use a two-threshold approach. First, one picks the PGA threshold, in our case 10% G. That's the threshold from which on a user expects damage. Second, one picks a probability threshold, in our case 0.4. Now we can calculate how likely it is, according to team, that the PGA threshold is going to be exceeded, and if it's more likely than our probability threshold, a warning is issued. We employ this strategy as it's flexible with regard to user needs, both in terms of the threshold from which on they expect damage, and also in terms on how they want to balance missed alerts against false alerts. Team can also be used to predict real-time shake maps. What we see here is again for the Nocia event, a shake map after 2.5 seconds. While the S wave hasn't reached many places, we already have a good view what the shaking might look like. We evaluate team in different hazard scenarios to get a good view of its capabilities. On one hand side, we use Japan, a region that's primarily defined by subduction events. On the other hand, we use Italy, where shallow crustal events cause the largest hazard. We collected the catalogue of 13,500 events from Japan and another one with around 7,000 events from Italy. Notably for Italy, we use all events in the year 2016 as a test set. The year 2016 contains the central Italy sequence, and in particular the Nocia event, which with a magnitude of 6.5 has a considerably higher magnitude than the largest training event. This poses a severe challenge to machine learning models. We primarily look at two evaluation metrics, precision and recall. Precision is the fraction of true warnings across all warnings that team issued. Recall is the fraction of true warnings against all cases where the PGA threshold was exceeded, or the fraction of true warnings among all warnings that should have been issued. We show precision recall curves for different level of shaking, from light shaking, 1% G in the leftmost column, to very strong shaking, 20% G in the rightmost column. We compare team to two baselines. First, EPS, estimated point source, a source estimation-based approach, and second, Plum, a traditional propagation-based approach. We see that team consistently outperforms both of those baselines, both Japan and Italy, for all PGA thresholds. For Japan, we also see that team outperforms, for all but the highest threshold, a GMPE. This is a GMPE that we actually provided with the catalog location and the catalog magnitude. It can outperform the GMPE because the GMPE does not account for all effects of the event, and this leaves an apparent aleatoric uncertainty, and team is able to better constrain this uncertainty. In the figure before, we considered every warning good if it arrived before the strong shaking actually hit. But in many cases, users will require a minimum warning time to actually take mitigation action. And this is what we show here. So on the x-axis, we show the required warning time. We consider each warning that arrives later than this time as a false warning. We see that the higher the required warning time is, the worse all of the methods perform. But no matter which warning time we choose, Team consistently outperforms, or for Italy performs at least on par, with the baseline methods. We also see patterns that are well known from literature. For example, that for higher thresholds, warning times are always shorter, or that Plum, the propagation approach, due to its localized approach, always only results in short warning times. Let me conclude. In this talk, I introduced the Transformer Earthquake Alerting Model, short TEAM. TEAM is a new data-driven strategy for earthquake early warning. It outperforms classical approaches across different hazard scenarios and is flexible regarding the set of stations and the set of targets. There are further advantages which I didn't discuss due to time constraints. First, TEAM can facilitate real-time processing, giving new estimate with each waveform sample that comes in. Second, TEAM can make use of data augmentation for the accurate prediction of very large earthquake, which we show in the example of the magnitude 6.5 Nochia earthquake. The TEAM paper is currently under review, but it's already available as a preprint on arXiv. You can find the link on the slide. I would also invite you to join the discussion on Tuesday, the 15th of December from 7:18 to 7:22. I thank you for your attention.